Okay, thanks, Andy, and thanks everyone for attending today. Like Andy said, this is some work that I did for a lantern project with AFS 11, and I'll talk about what that project is and then some of the larger scale results that we hope will come out of that. So some of the motivation and goals, not only of the lantern project, but also this talk today, are that AFS 11, so that's the analysis and nowcast branch, is required to both validate and verify systems that are prioritized by the field. And this is not on the developer end, this is more of a synthesis of forecaster opinions that we can take back to the developers and say, these are the things that people like, these are the things that people want, and then they are able to make modifications or implement those changes into future model systems. So the HREF was identified as one of the analysis and nowcast systems that the field uses regularly and wants to see improved. And all of us know that it's regularly used by us, especially during convective and winter forecasting. So that was the motivation for creating this evaluation. Now, the current version of the HREF is frozen in development, it's version 3, which we've had for a couple of years. That's frozen in development and there's not a HREF v4 that's going to come out. That'll eventually just be replaced by the RFS. So while this is an evaluation of the HREF version 3, all of the recommendations from this are going to be used to continue developing the RFS before it becomes operational. So anything that we're able to glean from forecaster feedback, from case studies, and from test beds will be implemented into the RFS instead of a future version of the HREF. So the HREF evaluation itself is comprised of a couple of different things. There was an HREF field survey that went out, and some of you were probably on the briefings. They did a quick briefing after those results were available. So that field survey is part of this evaluation. Then there are also some case studies that support some of the draft requirements that came out of that HREF field study. And then we also had a couple of people from AFS 11 that participated in a couple of the test beds, like the winter weather experiment, hazardous weather test bed, the spring experiment. And so those test beds were also looking at the HREF, and we were able to use some of their results for this evaluation as well. So I'll talk about all three of those things here pretty briefly. So a lot of you were on these outbriefs from the survey, so I won't spend a whole lot of time on it. But the HREF survey closed on the 6th of September of last year, so a little over a year ago. There are 193 total responses from the Weather Service, and you can see Central Region there was 53 of those responses. So the most responses actually came from Central Region. There were 6 draft requirements that were derived from the survey results, and I also liked the breakdown over here as a SIU. I noticed that there were 50 SIUs that responded, which is a little more than a third of all of the SIUs in the Weather Service responded, so definitely a heavy response from our SIU community. So these are the draft requirements. Like I said, there were 6 of them. And these are, again, just things that people want to see, things that people want to see improved from the HREF and eventually from the RFS. So the first one is pretty general, but just to define, develop or refine methodology for the HREF to improve the representation of these types of hydrometeorological phenomena. So by far and away, the first one was convection-related hazards. Most people are using this for their convective forecasting and are noticing places where perhaps convective events are not well represented, or at least not perfectly represented. So convection-related hazards was the first. Then winter weather hazards was probably the second most common answer that was given in those survey results. Then precip and QPF, and it was specifically noted in complex terrain, although also in flat terrain, QPF from model output is always challenging to represent. So that was a thing that people want to see better represented. Aviation hazards were also mentioned, mid-latitude cyclone-related events. We don't always think about the HREF as our large-scale forecasting system, but people do want to see some of those events better represented. Non-convective high wind events, and it kind of stopped there. That was the last one that came out of the field survey. But also related to non-convective high wind events is also fire weather events, which can be very impactful. So we actually added that one on based on some of the case studies. We also want to address the following forecaster needs with the HREF Ensemble membership. So specifically, people were pointing to the high-res FE3 model as being one of the problem members. Just anecdotally, we've seen several times that this has been a problem. So this was noted in the forecaster survey that there were some issues with convection intensity, convection amount, updraft helicity, and poor timing and improper location on the placement of convection. And this was new in the version 3 of the HREF as replacement for the NMMB, and doesn't seem to be performing a whole lot better than that member did. So that was noted as one of the low performing members. And then in general, just diversify the ensemble spread so that we're capturing some of those extreme weather events. This is a kind of unique ensemble system because not every member is the same core. So you do get a little bit more diversity in that ensemble spread than you would with a single core. But still there are some outstanding events, which we'll talk about during the case study portions, that aren't quite captured in even the extremes of the HREF. So this is a lot of words, and I apologize, but these are the following fields. We want to see both mean and some probabilistic information for all of these things. So you can see several of them are either precip or convection related, so CAPE and DCAPE, QPF, not only total amount, but also in different time frames, a phronogenesis parameter, surface wind and gusts. And a lot of times when the model predicts one of these wind speeds, what you actually observe is going to be a little bit different, but these are still the thresholds that people wanted to see from the model output. Then wind shear, again, back to that convection, 0 to 1, 0 to 3, and 0 to 6, and then also effective shear. Relative humidity at the surface, ceiling at 500 feet and 5,000 feet, and then also the flight categories and visibility at 1, 3, and 5 miles. So all of these things are just kind of wish lists for output that we want to see both in AWEBs and available online. We also, since we're creating a wish list, saw that people wanted more rapid updates. When you look at the SPC website, you're only able to see the 0Z and 12Z runs of the HREF. There are actually 6Z and 18Z runs of the HREF that are also available, but people were hoping to see the refresh rate for that increase to 8 times a day for the CONUS, since a lot of these high-res models are run more frequently than twice a day. And then also 4 times a day for Alaska, Puerto Rico, Hawaii, and then add a new domain for Micronesia and see that 4 times per day as well. We always want more data faster, so decrease the product latency to at most 2 hours, 1 hour is preferred. We know it can be a little bit slow trying to get all of the high-res models in, including the ones that go out to 60 hours, which delays the output of the HREF. So decrease that product latency, and then also extend the forecast lead time out to 60 hours. And this is not just a need from the survey, but also from some of the test beds as well. Then one wish list was to increase the spatial resolution to match the NDFD grid spacing. This isn't necessary because it's pretty close right now, but that 2.5 kilometer versus 3 kilometer was a wish list for some in the survey results. So we noted that as well. This one's also a lot of words, so I put the too long didn't read at the top, which is basically people like the SPC website and they want one that's official from the RRFS. So data availability in AWEPS, D2D and GFE, just make sure that the model parameters that are currently available on the SPC website are also available in AWEPS, both in the D2D and GFE perspective. We also want to make sure we can see all of the different ensemble members, both in AWEPS and in an online viewer. And then an original recommendation had been that we create another website that was similar to the SPC website, but that was hosted by NOAA, by AFS 11. And so I wasn't necessarily super jazzed about that just because we already have so many viewers that are in development now. So instead, these recommendations are possibly to be included on some of those viewers that are already in development, possibly like DESI. So just generalizing more to some sort of viewer that is operational, that includes HREF data and eventually RFS data. This is what people want to see. So ensure that whatever this viewer ends up being, that the HREF data matches the capabilities on the SPC website and the color tables as well. And ensure that the HREF model parameters that are available in AWIPS are also available on the viewer. So basically, we want AWIPS and the viewer to have the same capabilities and same information. And then also ensure that the 06Z and 18Z runs of the HREF are available on that viewer as well. So just wanting to see a little bit more in AWIPS, and then also kind of copy the SPC website into some other Ensemble viewer that includes HREF data. And then also something that the SPC website doesn't have, they do have the different sectors, but there is a wish list to be able to pan and zoom within that viewer, whatever that ends up being, and be able to manipulate those weather parameters. And then I think I mentioned this before, but in AWIPS have all of the color tables from SPC available in AWIPS. So those are the 6 draft requirements, just kind of the wish lists that came out of the field survey. So then the bulk of this report is finding case studies that support those draft requirements. So the draft requirements came from the field, but we want to make sure that we can support those with case studies and information from events that have happened. And there were a couple of cases that were already submitted to AFS 11 or were internally reviewed that we were able to find. But a couple of these, it's going to look like I'm picking on Kansas, because a couple of these are just cases that I remember, cases that impacted our area, because there really just wasn't a lot of information out there. People generally really like the HREF. And so when you're trying to find cases where the HREF maybe didn't perform as well, it's actually a little bit difficult to find. I even did a little bit of Twitter searching for people complaining about the HREF to see if I could find cases. And I actually did find a couple that way as well. So there are 12 cases. For time's sake, I'm only going to go over 6 today. So you can see the full list here. But the ones that are in black are the ones that I'm going to talk about today. And then the ones in gray, while they are included in that final report, I will skip over those for today. So the first one is December 15th. We've seen presentations on this already. We had that kind of large scale AAR that we did for Central Region. But just overviewing this case, basically we had a low probability of severe convective weather in the forecast, primarily due to a lack of signal in those individual cams that comprise the HREF. That's not the only reason, but it did impact the forecast in this case. And I'll show the graphic in a minute, but we had several reports of severe weather that were received in an outlook category lower than the slight risk from SPC. And some of these cases, it's going to look like I'm picking on SPC. I'm definitely not trying to. It's just showing how the HREF was influencing the forecast, just showing the impact of a bad cam forecast and the large scale impact that that can have. So it's also an easier way to look at it across forecast areas. So there are a couple of SPC graphics in here, but it's definitely not a criticism of their forecast. So in this case, again, I mentioned that we had the large scale multi-office AAR. Several of the offices that participated in that mentioned the CAM forecasts and how that may have negatively impacted their forecast. This case was pretty unique because the upper level forcing was actually really strong. And typically CAMs perform pretty well when the upper level forcing is strong, but in this case, that wasn't the issue. It does look like the model initialization or model resolution of CAPE was a little underdone. The forecast from the HREF at Topeka was about 200 joules per kilogram for the afternoon. And when we sent up our special 18Z sounding, the observed surface-based CAPE was 678. So likely an underrepresentation of CAPE that was factoring in here. And while neither the 0Z or the 12Z run forecast this convective event very well, there were minor improvements at 12Z. There was a little bit better forecast for thunder across, especially eastern Kansas. But since you have those time-lagged members of the HREF, it's kind of washing out that signal and washing out that improvement by including the time-lagged members. So this case really highlights that need for a better representation of high-impact events, and then possibly more diversity in Ensemble membership may have helped. In this case, the time-lagged members did negatively impact the forecast, but it doesn't necessarily mean that there shouldn't be some time-lagged component to the HREF. So this is the prob thunder from the 0Z on the 15th run and the 12Z on the 15th run, and that's valid at 0Z. And so you can see basically no probability of thunder across Kansas and Missouri from the first forecast, and just a hint of a possibility with the next run, but still not stretching very far through Kansas or Missouri. And then you can see the radar observations there at 0Z on the 16th with a pretty robust line of convection all the way from Missouri through eastern Kansas and down even into north central Oklahoma. So you can see that underrepresentation of that prob thunder. And this isn't always something that we would use for severe weather forecasting. It is interesting to look at. But in this case, since the synoptic winds were so strong, it was basically anytime we see lightning, we're going to have to issue a severe thunderstorm warning because our synoptic winds are 60 to 80 miles an hour. So looking at prob thunder in this case was a better indicator of where we might have severe convective weather. And then you can see the 24-hour probability of thunder just to eliminate any possibility that there were timing issues. So that's from 12Z on the 15th till 12Z on the 16th, and that's overlaid with the 6Z day one outlook, and then also storm reports. So you can kind of see where both the HREF and the larger scale forecast missed a lot of, especially the early convection that occurred even outside of 10% probability of thunder. The next case is the Marshall Fire case, and I really appreciate Paul Schlater's help with this and also his presentation a couple weeks ago on the guest speaker series that actually really helped compile some of this information. But the main issue here was a wind forecast. It was pretty cold. The RH was pretty well forecast, but what wasn't super well forecast were the extreme winds and especially off the high terrain. So the HRE was the one good performing member in this case. But the other HREF members were really reducing the ensemble mean and then the prob exceedance values. So you basically have one high performing member and then the rest are kind of dragging it down. In reality, and a lot of you saw this presentation, there were over 100 mile an hour winds that were observed for several hours. And Paul showed a great graphic of a couple of sites from their employees and other local sites where there was a greater than 80 mile an hour wind speed difference observed over less than 10 miles. So that's really difficult for a model with a 3 kilometer grid spacing to resolve. And so it makes sense that it wasn't able to resolve this real well, but it was a case where the HREF didn't represent the wind forecast very well. And a lot of this was due to terrain as well. You have that persistent mountain wave that was locally enhancing the wind, and it lasted a lot longer than would normally occur and would normally be forecast. And the end result was damage or destruction to over 1,000 homes and 30 commercial buildings. So a really high impact forecast here. And you can see I was only able to grab the ensemble max and ensemble mean. So you'll just have to trust me that the ensemble max was from the HRE. And you can see kind of the Louisville Superior areas circled there in white. The circle's a little big, but it's just so that you can see it. But you can see the HRE did stretch those higher winds. This is in miles an hour, so 70 to 80 mile an hour winds in the Superior Louisville area versus the ensemble mean, which is more like 40 to 50. So one of the members got it, but if you're looking at those mean values or those prob exceedance values, you may not catch the high impact event, and especially the non-convective winds and that impact on the fire weather forecast. The next case is also from the Boulder area. This was internally reviewed by David Bargenbrook out at the Boulder office. And this is a case where not only was the snow forecast underestimated, but terrain was also an influence, which is always interesting for modelers to look at to see how that terrain is being represented in a model forecast. So the snow amounts in this case were underestimated by several inches in the HREF, and the snow rates were also underestimated. They did end up observing 2 inches per hour, and that was during the afternoon. So that was when some of the traffic was starting to pick up in the afternoon rush. They did have shallow upslope flow, which was locally enhancing snow amounts in the foothills. And again, they had quite a few impacts of traffic, total amounts of 9 to 10 inches. The heaviest snow was on the north side of the Denver metro area, but still those 2 inches per hour were observed, especially on the west side of the Denver metro, again, during that kind of afternoon rush hour. And so you can see the HREF ensemble mean, the 24-hour snowfall is on the left. The probability matched mean is in the middle. If they look identical to you, I understand. They're actually not much different in this case. Some indication of higher snow amounts, but that it's more tied to the high terrain and doesn't spread very well down into the foothills and the western side of the Denver metro. So not a big enough footprint, and the amounts are also too low in this case. So just a case where possibly terrain influence was not picked up by the models, and also just a general underestimation of both snow amounts and QPF, which I didn't show in this case, but QPF was also underestimated, which was part of the problem here as well. We also have an aviation case. This was submitted by Roland Nunez at the AWC, and this was occurring along the Gulf Coast of Texas. So we have a issue with the representation of this high impact aviation event. Possibly more diversity in ensemble membership would have helped, and also shows a need for whatever online viewer or in AWIPS to have these flight categories and these different ceiling heights, because that's not available on the SPC website. It is on the EMC website, but you kind of have to go digging for it to find it. So all of these things are captured by this event. So you have HREF probabilities of IFR and LIFR, if you knew where to find them, are significantly underestimated inland. And then the IFR or lower ceilings were actually observed for up to 10 hours. When I looked at some of the impacts of this forecast, the TEFs were not able to provide a whole lot of lead time for the LIFR ceilings. They were indicating IFR, but it was a little bit later in the morning and not quite low enough either. So the offices kind of had to play catch up as some of those observations started coming in. And there were impacts to the Houston area airports. I did another Twitter search for this, basically just looking for people complaining about flight delays, and did find that the Houston area airports were pretty impacted by this event as well. So you can see on the left the HREF probability of those IFR conditions. This is at 9Z, so basically out over the water, and some pretty low probabilities of those IFR conditions inland. And then on the right, you can see the surface observations for the same time. So at 9Z again, those IFR conditions spread pretty well inland and include the Houston area. So there aren't a lot of observations out over the water. You can see that there were some IFR conditions on some of those buoys off the coast of Louisiana. So it's not necessarily that it failed to forecast those lower ceilings over the water. It's just where people live and where the impacts are, that it wasn't spreading quite far enough inland. The next case is another Kansas case, another severe weather case. So this is the 11th of June in 2022, and this was the Symphony in the Flint Hills DSS event. So some of you are familiar with this case. And the basic problem here is that most of the high-res models, most of the cams that comprise the HREF were developing convection in the right place and about the right time in southeast Nebraska, but then we're pretty unable to figure out the convective evolution of those storms as they moved either south or southeast. So most of the cams had that cluster developing, kind of bowing out into an MCS type structure and moving more to the southeast. There was only one member, which was the NAM nest, that had a southward moving cluster. But due to timing differences, location differences, the HREF probabilities really started to drop off after convective initiation. And where they were highest was along the Kansas-Missouri border, which did influence the SPC outlook and also influenced local forecast offices, local staffing decisions, all of those things. And the severe weather didn't end up impacting that outdoor symphony concert, Symphony in the Flint Hills. If you're not familiar with it, is an outdoor symphony concert. It's a pretty big gathering of people, and it's always out in the middle of nowhere because it's in the Flint Hills. So usually pretty isolated from any shelter. This case was pretty unique because there had been some rain a couple of days before, maybe even the day before. So the parking was well separated from the concert venue, and they were actually having to bus people over so that they wouldn't be getting stuck in the mud. So even more vulnerable than usual for this case. So you can see the HREF 24-hour probability of updraft helicity that exceeds 75 meters squared per second squared. And this again is from 12Z on the 11th till 12Z on the 12th, and it's overlaid with the D1 outlook. So you can see those highest probabilities, while they do start to drop off after convective initiation, do spread more southward into like the Kansas City metro area. I mean, you can see the enhanced risk kind of mirrors those highest probabilities for UH along that same corridor. And then the storm reports are the dots and squares that you can see. So several tornado reports that went all the way south into the Manhattan area in Kansas, and some pretty significant severe weather that occurred just on the edge of that outlook area and even on the southwest edge as well. And here's a picture from the Symphony in the Flint Hills, as well as a Facebook post. So the event did start. This was on-site DSS from NWS Wichita. I can't remember if it was on-site or if it was just supported by one dedicated person. But they did have support from the Wichita office and were able to make the decision to get everyone out. They obviously saw it coming, but it wasn't necessarily in the forecast that morning, and did have to play a lot of catch up with convective evolution for this case. So people were able to get out and get to safety, but you can kind of see that pretty significant looking shelf cloud moving over as traffic is still exiting the parking area for that concert. So we're skipping a couple of cases if you're following along with the numbers, but the next one is a winter weather case. This is again from the Central Plains, Kansas, Missouri on the 17th of February 22. This came in the wake of several events where we were forecasting a little bit more snowfall and some lower amounts occurred. So there was a little bit of carrying that as we moved forward of a lot of these events have not been working out. Why should I believe this one? So that was an influence that was kind of sitting in the back of everyone's mind. But in this case, the Kansas City metro area and also portions of the Topeka area received 8 to 11 inches of snow. The HREF was initially indicating higher amounts and higher probabilities greater than 8 inches of snow in the KC metro area, but then started to back off. So some of these original forecasts were advertising the higher amounts and then started to back off as the event got a little bit closer. That really impacts forecaster confidence, especially in the wake of several events where this writing's on the wall right before it starts, but you have those higher amounts to begin with, and then they're steadily decreasing once the forecast is already out. So you could read it in some of the AFDs as I was looking back at those, that you could really see that decreasing confidence based on some of these decreasing amounts. And there is the expectation that the forecast is going to get a little more certain as it gets closer. That can obviously be impacted by more model solutions coming in that may not increase your confidence, but the HREF is fixed. You have the same number of model forecasts available to you regardless of how close to the event it is. So seeing those decreasing amounts really impacted confidence. So you can see on the left, that's your probability of exceeding 8 inches from the 0Z run on the 16th. And then the center panel is the probability of exceeding 8 inches from the 0Z on the 17th run. So big decrease for the KC Metro, a little bit of a southern shift to that band. And then your observed amounts are over there on the right. So you can see a broad swath of 8 to 12 inches that went through Ottawa into the Kansas City area. And then another big swath of higher amounts also north of the St. Louis area. So while this isn't a horrible forecast, that decrease in confidence, that decrease in probability really impacted that forecast. And while it still was a good forecast and we were still advertising those higher amounts, you could really see some of that decreased forecaster confidence and messaging in the AFD talking about more like 3 to 6 inches, like just not really believing those higher amounts due to how the models were trending and how that confidence was changing. So those are all the cases that I'm going to go through. So then we'll just talk quickly about some of the test beds and the results from those. So there were a couple of different test beds from the Weather Prediction Center from WPC. During the winter weather experiment, the HREF was not officially evaluated. I think they looked at it a couple of times, but it wasn't officially evaluated. And the biggest reason for that is that it doesn't go out far enough. So when you're doing the WWE, if you've ever participated in it, you really want that day 3 through 1 progression. So you want to start with the system on day 3, start looking at things. evaluated again on day 2, and evaluated again on day 1, so that you have that continuity of the forecast process. And since the HREF only goes out to 48 hours, they weren't able to look at it on day 3. So that was part of the reason it wasn't used. It also lacked a necessary variable that the WWE uses for forecasting, which is the change in snow depth. So you get obviously snowfall amounts from the HREF, but you're not getting that change in snow depth that you can get from some of the other models. So they weren't able to look at that. And then they were just intentionally evaluating other models, which includes the RFS. Obviously not operational, but the current version of the RFS. They were wanting to look at that, as well as some other CAMs that are developed by participating organizations like Utah. So it wasn't officially evaluated, but it does give us some information about some needs in the future, so that it maybe could be included. It was used in the flash flood and intense rainfall test bed that was in 2021. I think they had another one in 2022, but the results from that aren't available yet. But basically they were looking at other CAMs, mainly wanting to focus on that FV3 model core, the eventual RFS version, but they were using the HREF as a benchmark. So everything was compared back to the HREF as kind of this gold standard for what we were wanting to see from the other CAMs. None of the FV3 based CAM ensembles outperformed the HREF. They presented several cases where the HREF didn't necessarily nail it either. And one of them is actually one of the cases that I didn't present today, but included in the evaluation, where some of the rainfall amounts were underestimated. But it still did perform better than the other CAM ensembles that they looked at in that test bed. And they did note that the RFS was under dispersive, which is probably going to be a problem with that single core. And they recommended that we continue to work on and continue to develop the RFS, and noted that it wasn't quite ready to go. Then the hazardous weather test bed from this spring, those results were just released about a week or maybe 2 weeks ago. They were also intentionally evaluating other CAMs, but using the HREF again as a benchmark, kind of comparing everything against the HREF. And part of that is that one of their goals was to identify a strategy within this UFS framework, i.e. the single model FE3 LAM, that performs as well or better than the HREF version 3. So they're basically looking for a replacement for the HREF within the NSEPS production suite, and looking to see if anything is getting close to that during the convective season. So they made comparisons between the HREF and then the RFS P2E, which is the prototype that will eventually be implemented as the operational RFS version 1. Then a couple other iterations of the RFS with slightly different physics, radiation schemes, just some minor modifications. And there were cases where not necessarily all of these iterations of the RFS were available. The HREF was available for every case, but the comparisons weren't direct in all of them, just because some of these specific iterations of the RFS weren't available every time. So when they looked at subjective ranking, so this is what did forecasters feel was the most useful during the hazardous weather test bed, and this was for forecasting hourly maximum fields of severe weather over a mesoscale area of interest for the forecast hours from 13 to 36 hours. So this is comparing the HREF to the other versions of the RFS, and you're looking for a low number. You're wanting to rank it as first. So you can see the reason that there are two different plots here is that the one on the right is a case where it was the RFS mixed physics was not available. So it's just a little bit different comparison. In those cases, they didn't want to lump them all together and have a different sample size for one of them. But you can see in both plots, the HREF and the RFS P2E are pretty close. HREF slightly outperforms RFS in that larger sample size, and then the smaller size RFS is ranked just slightly better. But overall, much closer than we've seen in the past for things in comparison to the HREF. So the HREF and RFS P2E were ranked, top ranked most frequently. And again, this is a subjective rating. The HREF ranked number 1 43% of the time, and the RFS P2E ranked number 1 31% of the time, and the others were much lower. People did note timing and probability magnitude differences in the ensembles. They noted that the HREF was the one that had the most ensemble spread, which is going to do a better job of capturing some of those extreme events. The performance and how the forecasters ranked it really depended on whether they were comparing the LSRs to updraft helicity or to wind diagnostics. So both of those can kind of be used, especially depending on what type of severe weather was occurring. So it kind of depended on what they were comparing to those LSRs, how they ranked things. But the similar subjective scores between the RFS and the HREF gave some confidence that version 1 might be able to be transitioned into operations here sometime soon. Then they also looked at some of the forecast parameters. So this is for similar type scenarios, but looking at some of the individual variables. So you can see a comparison between the HREF and RFS P2E. So the ones on the bottom, or the negative numbers, are the ones where the RFS was worse than the HREF. And then the ones with the positive numbers, are the ones on the top, are the ones where the RFS was rated as better than the HREF. So you can see basically temperature is a little bit worse in the HREF, but the dew point is better in the RFS. So I might have said that wrong. So the HREF is better performing at the temperature. The RFS is better performing at the dew point. And we're looking mainly at the 17 to 20 UTC, not just because this is a common time for convective initiation, but also because it's the strongest signal out of any of the other time periods. So you do see an improvement with the RFS for the dew point and possibly the surface-based CAPE, which are both noted issues with the current version of the RFS, or with the HREF. So something that we might want to see improved when the RFS is released. So that's good news, but you also have that payoff of a worse temperature forecast, which is why you see kind of that huge box and whisker for surface-based CAPE, since both of those parameters are an influence on surface-based CAPE. So a little bit of a payoff here, but at least some improvement with that surface dew point, which is, again, something that was noted as a problem with the HREF. And you kind of lose that signal as you go into the evening. Boundary layer may be a little more similar between the two. So you really see that highest signal during the afternoon hours. So just to summarize the HREF evaluation, HREF continues to be a high-performing ensemble, although that high-res WRF FE3 member continues to be the most problematic member and needs to be addressed with future iterations of the RRFS. There's a need for an online viewer with more variables and thresholds for probability of exceedance, and also that pan and zoom feature. Overall, the look and feel of the SBC website is desired for any future viewer that is implemented. And then our online HREF requirements may be implemented into an Ensemble viewer that's already in development, like I mentioned before, DESI, the WSOP viewer, maybe even Wave. Something that's already in development, I think, would be more appropriate than developing yet another website to send people to. So some of the recommendations for the future RFS, these draft requirements that we put together will be packaged along with requirements that were developed by AFS 11 for the HRE. And those are quite a bit further along. Those aren't draft requirements, those are in their final recommendation. And it's the most popular regional deterministic forecast system. So the HRE is the one that's chosen to be combined with the HREF for recommendations for the RFS. And that'll be translated into a set of requirements for the first version of the operational RFS. The operational RFS will have to perform at least as well as the current HREF, as well as address some of its shortcomings for it to be well received and used by the field. And the latest implementation timeline, this was presented at NWA. It's possible that this could continue to slide just based on development, based on how these requirements are received, all of that. But currently, the implementation timeline for the RFS version 1 would be the second quarter of fiscal year 24. And then the retirement of the HRE and the HREF is slated for quarter 3 of fiscal year 24. So still got some time, but all of these things will be carefully considered. All of the shortcomings of the HREF, as well as any current versions of the RFS, will all be considered and addressed before this becomes operational to the field. So this was supposed to be the place where I found all of my cases to to be able to use in the HREF evaluation. This is the VLAB feedback forum from AFS 11. And it looks very sad. You can see the only post here is from Eric, who's a former AFS 11 employee. And there are no responses, and only 20 people have seen it. And there are no other posts in here. So if you have a problem with the HREF, if you notice a case where something wasn't well represented, please post it here. I've got the link here. You can also search for it in VLAB, just HREF feedback forum. Please post it there and it will be addressed. These are just draft requirements. So the HREF is going to go through a final evaluation and is currently being submitted to cards. So it's still in process. You can still provide your feedback. And this is the easiest way to do it. My lantern's wrapping up. But whoever takes over this project in the future, they're just in the process of hiring some new employees at AFS 11. They will be able to see it through this VLAB feedback forum. So if you have further feedback on the HREF and things that you want to see from the RFS, please post it here. And that is all I have. I'm not sure if there are any questions, but if you have any, I'd be happy to answer them.